Yes, class. Am I audible to all of you? Padil, Deborah?
Yes.
All right, all right.
Yes,
So,
ma'am.
yes, start with the revision. So, we've already completed the syllabus. Syllabus was over, as I have already mentioned to you that we'll be having the revision classes starting from modern physics itself. Because modern physics, we require a lot of practice. So, what we'll do, we'll try to cover the major theory portion also, as well as the revision part also of the numericals, because lots of numericals are there which are pending from modern physics itself to be dealt. So that we'll do, but a thorough revision is required. So you people also should be attentive while answering, and I am there to help. So let's start with it. Dual nature of matter and radiation. Here we have the concept of free electrons in metals. Some things are there which you should remember, which I'll be discussing with you. Firstly, before we start with anything, you should be aware of the fact what is 1 electron volts conversion into joules. So yes, what is it? How do you convert 1 electron into joules? You multiply it by 1.6 into 10 to the power
1.6.
minus 19. Very good. Yes, correct. This is electron volt is commonly used unit of energy in the atomic and nuclear physics. So that's why this will be given in the modern physics section and the semiconductor especially. So free electrons, when we talk about the free electrons, see, these are all the shells of the electrons. All of these are the shells of the electrons. So in metals, electrons in the outer shells, if we talk about the electrons in the outer shells of the atom, these electrons are loosely bounded. They are loosely bounded. So they keep on moving like free positive ions in the lattice. So that's why we call all of these electrons as the free electrons. All these electrons are called as the free electrons. Why? Because they are loosely bound. And if they are loosely bound, it means they have the tendency, if sufficient criteria, whatever their criteria is, if that is fulfilled, they'll be able to free themselves. So every electron which we are calling as the free electron should have a minimum value of frequency, minimum value of wavelength, minimum value of energy, and minimum value of potential. This is the basics to everything that we'll be studying. Every electron has all of these maximum values. If it is a free electron, if it's a free electron, it has the tendency, it is loosely bounded to the nucleus. You don't have to write down everything in the class. I'll be just telling you to note down whatever points. Only that you need to write, otherwise nothing. Because you already have the notes with you. Numericals we'll be practicing. Minimum 10 numericals are there from dual nature to be dealt. So attend the revision classes properly and write down everything, whichever things I mentioned properly. So yes, so minimum for every electron, minimum value of frequency is required for the electron to be free. Minimum value of wavelength is required by the electron to be free. Minimum value of energy is required by the electron to be free. Minimum value of potential is required by the electron to be free. Now, when all of these we are talking about, the frequency, the wavelength, this we call it as the threshold frequency. So that's why all of these definitions are very important. The definitions of threshold frequency, threshold wavelength, work function, all these are very important. So this is the threshold frequency. This becomes the threshold wavelength. This minimum energy we call as the work function, and minimum potential we call as the stopping potential. So these are the basics which all of you are already aware of. Now, in the class also, I discussed some things with you. Firstly, which included this that I have discussed, minimum values. Now, definitions are important. Coming to the types of emissions which are available, which are possible. So first is the thermionic emission. What is meant by the thermionic emission? When we use the term thermionic emission, basically thermionic emission means that when a metal is heated, its free electrons are already present. So its free electrons get sufficient thermal energy and they can overcome the surface barrier. So this method of the removal of electrons is called the thermionic emission. And the electrons, we call them as the thermions. We call them as the thermions or thermoelectrons. Let me write this separately here because lots of things are written over here. Just keep on paying attention to it. So how do we release the electron? Release of electrons. So first process is through thermionic emission. That is, electrons are released by the thermal energy. And we call these electrons as the thermions. Or you can even call them as thermoelectrons. Thermoelectrons. Second process which is available, this is known as field emission. Or we also call it as cold cathode emission. Now see, what is meant by field emission? Field means only the electric field. We are talking about the electric field. Field means itself the electric field. So when a metal surface is subjected to very high electric fields, when I use the term very high electric field, it means in the order of 10 to the power 3 to 10 to the power 8 volt per meter. So electrons are emitted from it, and we call this as the cold cathode emission. Because one more thing, that this method is less efficient. This is dangerous also, and it is less efficient. So this is not used much. Thirdly, we have the secondary emission. We have the secondary emission. So in secondary emission, when a fast moving electron or when fast moving electrons strike metal surface, so they transfer some of the energy to the free electron of which is present on the metal surface. So as a result, what happens? As a result, the energy of the free electron, this crosses the work function, this becomes more than the work function, and they get ejected from the metal surface. So the emitted electrons, these electrons which are emitted, we call them as the secondary electrons. These are called as the secondary electrons. And this method of removal of the electrons is called the secondary emission. Lastly, we have the photoelectric emission. So in photoelectric emission, basically how the electrons are ejected, they are ejected through the help of electromagnetic waves, that are the electromagnetic radiations of sufficiently high frequency are incident on it. The emitted electrons, now they'll be called as the photoelectrons. These electrons which are emitted, these electrons are called photoelectrons. All right. So it's a process in which electrons are emitted from the metal surface when electromagnetic radiations or these electromagnetic waves. You all are already aware of the entire electromagnetic spectrum. You are already aware of it. So you know which waves I'm referring to. You know the frequency and wavelength also now. You know the exact order also. All right. So these are the 4 types of emissions that are taking place, 4 types of emission which are going through. Now see, let's focus. I have already told you, out of all of these emissions which are occurring, The last one, that is the photoelectric emission, is very important. We talk about the electromagnetic waves, entire electromagnetic radiation spectrum is important. We'll be dealing with that only. So you can get a separate question to describe the phenomena of photoelectric effect. Now, basically, how all of the experiments started, let us just focus on that so that you will be also able to know which conclusions I am referring to. All right. So, firstly, was the experiment done by Hertz. The frequencies SI unit also we use it as Hertz, the same Hertz. This was given by Hertz only. So initially Hertz did the experiment. You don't need to remember this so much in detail, Hertz observations, because this is not a part of your syllabus now. So this is just so that you understand everything in detail, and it's mentioned in your textbook. So you should be aware who gave it. So earlier, very earlier in the 1800 something, I don't know the date, Hertz did some experiment. All right. So he was the one. Hertz's observations were very important because these observations only helped us to get the knowledge about EM waves. That yes, in photoelectric emission, EM waves, EM radiations are important. All right. So high voltage sparks he used, he passed them through the metal electrodes. And one more thing, the rays out of the EM waves which he used, those were the ultraviolet radiations. Out of the entire electromagnetic spectrum, the rays he was using were the ultraviolet radiation. So ultraviolet radiation used to fall on the metal surface, and then charged particles were emitted, but by that time these charged particles were not termed as electrons. Like right now we know those negatively charged particles would have been electron, but that time it wasn't known, so it was just said that some charged particles are getting ejected, some charged particles are present. But now we know that these negative, because these are negatively charged particles and they are electrons and nothing else. But through this small, tiny experiment, can something be concluded? Nothing was concluded. At that time, even it wasn't, nobody was sure about the fact that whether electrons are present or not. Right? So, this experiment was left here only, but some ideas were given. Then the term which is very important for you to remember is Hallwash and Lenard's observation. Then came Hallwash and Lenard. They were very, very important in the entire experiments did for the photoelectric effect. So basically they were there during the time of Hertz, but when Hertz left the experiment, Hertz concluded this experiment, just high voltage sparks experiment he did. So some things were missing. So that was taken up by Hallwash and Lenard. Both of them took the experiment. So basically they took a zinc plate like this. A zinc plate was kept, and again, because they knew that ultraviolet radiations only are going to help, so they used UV light itself, and this plate was the zinc plate. This plate was the zinc plate, and this was kept into an electroscope for detection. This was kept into an electroscope, and this was strapped and a part of circuit so that this is insulated, and all in all, like this it was done. All right. So when this experiment was done, here, this experiment, at least, this gave us the conclusion about threshold frequency. Through this experiment, we had the first idea about threshold frequency. We had the first knowledge about threshold frequency. What is meant by threshold frequency? That incident radiation has a minimum value, which is called threshold frequency, and no photoelectrons are emitted below this. All right. What did they notice? That when a frequency was set, electrons used to get ejected. If this a little less than this frequency was set, electrons did not get ejected. Till the time it was equal to or greater than this, then only it was ejected. Right? If it was less than this, they were not rejected. If it was greater or equal to, then only electrons were rejected. So they were the ones who gave the definition about threshold frequency. All right. And then the term, at least, photoelectrons, photoelectric effect, because by that time, J.J. Thomson, through his entire experiment, they were doing the watermelon, plum pudding experiment, all these Rutherford, J.J. Thomson, all these were giving. So by that time, he was the one who introduced those negative particles as electrons. And that time only these were termed as the photo electrons. By that time only, because by that time, this experiment was also going hand in hand. So when the threshold frequency definition was given, the current was termed as the photoelectric current, the electrons were termed as the photoelectrons, and the entire process was termed as the photoelectric effect, photoelectric emission. So this was done. Now, some things were still left. Some experimentations were left. This was the final conclusion, that yes, photoelectric effect exists. This photoelectric effect exists in nature, but modifications and experimentations weren't done, right? So what happened? Hallwash's work was over. Linard stayed. Linard was still there. You must have heard of Millikan oil drop experiment is very famous, R.A. Millikan. So then the extensive study of this entire photoelectric effect were done by these two. And what all things they could conclude, all the graphs which we had seen separately. After in the timeline, they came, the entry of Linard and Millikan came. So what did they show? Firstly, they told about the photoelectric current and the intensity of the graph. That as soon as the intensity of the graph was increasing, it was noticed that he made this entire experiment. Basically, what was there in the, not he, both of them, Linard plus Millikan, it was their experiment. So a positive photosensitive plate was taken, a quartz window was left open for the sun rays, for the light to enter. This another plate was the collector plate, and the entire tube was the evacuated glass tube. So when the light rays strike this metal photosensitive plate, electrons were ejected, which was detected by this ammeter, which measured in microamperes. So the current that was flowing within the circuit, it was the photoelectric current. This was measured, and the voltage was measured by the voltmeter. And to regulate the amount of photoelectric current, rheostat was developed. So this modulated the resistance, the amount of current. Because see, the amount of resistance you keep on increasing, value of current would decrease. So this this was already given by Ohms by that time. So we had the entire concept of rheostat, battery and key. So first conclusion that was given was that as soon as you increase the number of electrons and you increase the intensity, number of electrons will be increasing and the photoelectric current will be increasing linearly. So photoelectric current is directly proportional to the intensity. This was the first conclusion. Second is the effect of potential. This graph. See, this graph which we had already seen. This second graph. First graph is clear? Yes or no? All right. So see, coming to this graph, this graph was done to check the effect of potential, to see how potential regulation will modify the current. So basically, the frequency was kept fixed. Frequency was fixed, right? Intensity was variable this time. Now, positive potential, that is, this was the accelerating potential. As soon as the potential was increasing, that is, the accelerating potential was there. So photoelectric current increased with the increasing accelerating potential. See, it was increasing with the increasing accelerating potential. And photoelectric current becomes maximum and it does not increase further with the increasing accelerating potential. And this maximum value of current, we call it as the saturation current. If you increase the intensity, the magnitude will rise further, photoelectric current will increase because it is directly proportional to intensity, so it will increase. But again, it will reach a maximum value, which we call as the saturation current. Same thing like this. All right. So there is a retarding potential for which the value of photoelectric current becomes zero, which we call as the stopping potential. You call it as the cutoff potential also. All right. This was the second graph that was concluded. Talking about the third graph. Coming and talking about the third graph. That is the effect of frequency was now studied, effect of intensity was seen, effect of potential was seen, now effect of frequency. See, Leonard and Hallwash, both of them did the experiment, they gave you the conclusions about photoelectric current, but nothing was proven about these modulations, like if the frequency increases, if the intensity increases. So for that purpose, Leonard and Millikan had the experiment. Now, for the effect of frequency of the incident radiation, this time we kept the intensity fixed. Intensity was kept constant this time. Or it was adjusted, the frequency was adjusted in a manner that every time you obtain the same saturation current. Because saturation current concept is already clear to you. So potential gradually decreased to zero, where photoelectric current becomes zero. So this was observed. Basically, when the frequency increases, this entire graph gave us which conclusions? It told us this, all the implications of the graphs are very important. So this implies that the greater frequency of the incident radiation, greater the frequency. Look, one thing I'll tell you. Frequency multiplied to wavelength gives the speed. All right. If frequency increases, speed increases. Agree? Formula of kinetic energy is half mv square. So kinetic energy is directly proportional to square of v. So if frequency is increasing, velocity is increasing. So velocity is increasing, kinetic energy will increase more, right? The maximum kinetic energy will increase, and kinetic energy has a formula with stopping potential as EV naught. This formula as EV naught. So if kinetic energy is increasing, stopping potential will also increase, because this and this, they are directly proportional. Clear? So what happened in this graph? This was the conclusion that greater is the retarding potential required to stop the electrons completely, because velocity was more. Why? Because frequency was more. This was the relation. This was the conclusion about this entire graph. Understood? These were the conclusions from the graph, if we are talking about all the conclusions. So what all things do you conclude from here? From Leonard and Millikan's experiment, many things were given. Firstly, some conclusions. Let me write you some conclusion. This you can note it separately. I'll give you time to write it down. Right now, please do not write down anything. Please be interactive. Try to learn itself in the class. Any doubts, if you have, let me know. I'm revising every point in detail. Some things I'm telling extra which I didn't discuss even in the class time. So pay attention to all the words. Anything you want me to repeat, let me know. I am there. So conclusions were basically, one conclusion that was observed was that this stopping potential, this increased linearly with the frequency. Reason I have told you, reason is simply that frequency multiplied to wavelength gives velocity. If velocity increases, kinetic energy increases. Reason is kinetic energy is half mv square. kinetic energy is equal to charge into stopping potential. So if kinetic energy increases more, stopping potential is going to increase more. So this and this ultimately become directly proportional to each other. That was the first conclusion from the graph. V naught is directly proportional to the frequency. Understood? Frequency, this is not the threshold frequency, this is the frequency of the incident radiation. Secondly, second conclusion that was observed, that for the minimum cutoff potential to exist, that is threshold frequency to exist, as soon as threshold frequency is achieved, the photoelectric current becomes zero. So for that, when photoelectric current becomes zero, stopping potential is also zero. That is the cutoff potential is also zero. This was also one very important conclusion. Apart from this, there were two more conclusions drawn, which we have already discussed in the class 1, that the maximum kinetic energy is directly proportional to the frequency. This I have told you. And another conclusion was that kinetic energy maximum was independent of the intensity of the graph. All right. So these were the conclusions, all the possible conclusions which we had seen. It is independent of the intensity and directly proportional to frequency. So out of all of these, the laws of photoelectric effects were statutated. Right? All the through these laws were based on the Leonard and Millikan's conclusions. When we talk about the laws of photoelectric effect, first law basically tells us that for a given photosensitive material and the frequency of radiation, we should be knowing that the photoelectric current is directly proportional. It's directly proportional to the intensity. Why? Reason behind this is that the number of electrons, which we call as the photoelectrons, increases, so current increases. See, saturation current is directly proportional to intensity of incident radiation. Not only photoelectric current, even the saturation current is directly proportional to the intensity. All right. Second is that it gave us the definition of threshold frequency. So when the laws are coming after explaining this point, you should write down the definition of threshold frequency. This definition you should be able to write. All right, definition of threshold frequency. Then this was observed, the graph that I plotted, that kinetic energy is directly proportional to frequency, but kinetic energy is independent of the intensity. It is not proportional to it. And last one, that the photoelectric emission is an instantaneous process. Means when the light strikes the metal surface and the electrons become loosely bounded and they become their threshold values cross and they become independent and get ejected. So that time lag between the incidence of light radiation and the emission of the photoelectrons is very small. This is approximately 10 to the power minus 9 seconds. So we call this process as instantaneous process. This is instantaneous process. That's it. This is the instantaneous process. So we'll see Einstein theory of photoelectric effect also. Some additional things if it is required. Mostly the things we had discussed. So these were, we'll talk about Einstein's photo, but before that you should write down all of these points because these are separately written. And some extra things are there which we didn't discuss in the class. So start writing this page. Yes, class. Now, apart from this, we had the Einstein's theory of photoelectric effect. So, Einstein's theory. So, firstly, there was a conclusion that was drawn by Einstein was that photoelectric emission that occurs. Let me write down so that you can copy and you'll have all these notes with you. This photoelectric emission that occurs, this is not just because of electrons which were interacting. Einstein, see, Hertz gave certain conclusions and left the experiment. Then Hallwash and Lenard, they did their experiment and they gave some conclusion and they then left. Then Lenard with Millikan gave the entire modulations and modifications of the photoelectric effect. Further, Einstein, whatever theories were left from this, moving electrons, he brought these terms into actions. So he said that it's not just the electrons which are acting. There are interaction of two particles which are acting. One is a photon. Photon is present in the incident radiation. The photon, this is present in the incident radiation. All right. It's present in the incident radiation. And second is the electron, which is present in the metal. Metal means the photosensitive metal. So photoelectric emission is the result of the interaction of these two particles. That is the photon of the incident radiation and electron of the photosensitive metal. This was the first conclusion. Secondly, he introduced the entire complete definition and concept of work function. So that's why I am telling definition of work function can come separately as well. All right, definition of work function. Then he told the fact, see, energy is directly proportional to the frequency. So we have a constant here, that is the Planck's constant. This value of Planck's constant is 6.63 into 10 to the power minus 34 joule seconds, all this. So this is, when we talk about this, this is about the incident radiation. This is of the incident radiation. Incident radiation means if this is the metal surface, this is this radiation which is falling. This is the incident radiation. All right. Now, total energy which is present. This is not just the total energy. This, a part of the energy, see this incident radiation's energy, this is also made up of two portions. He basically introduced the main contribution by Einstein was this, that he said that the incident photon or incident energy, that was h nu. This was made up of two things. A part of the energy of the photon was used in liberating the electron from the metal surface. That is, minimum amount of energy was required to liberate it. That was the concept of work function. Secondly, the rest of the energy, the remaining energy of the photon, was used in imparting the kinetic energy to the ejected electron. Because it was moving, so kinetic energy was required. Hence, you have the equation which we have already studied in our classes, that energy of the incident photon is equal to kinetic energy plus the work function. And this also I have told you earlier as well, that for energy you can use the formula h nu or hc by lambda. For kinetic energy you can use half mv square. For maximum kinetic energy, this is Vmax square, or electron into stopping potential. Work function is the minimum amount of energy, so minimum amount of frequency will be required. Minimum amount of frequency is called the threshold frequency. So h nu naught is used, or hc by lambda naught is used. Like this, we have all the energies which are present. All right, now any combination will be, we have lots of numericals for this. So we'll be using it. Different equations, combinations of equations will be constructed. Especially the common equation that is used is this. H nu minus nu naught is equal to the kinetic energy. This is also very common. Or any of these can be used depending upon the question, as we have discussed. One graph is left to be discussed. First, write down it from here. Then I'll discuss the graph. Okay, the last thing, the discussion of the graph. Then straight away in the next class, we'll be doing all the numericals. One thing, tomorrow at this timing, I'll not be able to take your class. So just let me know, are you both available in the morning? Okay, not morning, then a Monday. Okay, I'll just check when your timings are free. Just let me know. Just reply in the chat column at least right now, so because your voice isn't coming.
Ma'am, in the morning or on Monday?
Monday.
Yes, ma'am.
Monday evening. Do you people have any class?
Monday, what timing, ma'am?
Evening, any timing in which you people are not having any class. Just 1.5 hour class that I have to take. Numericals I have to complete.
Yes, ma'am, but then can you take it before 10:30 IST?
Yes. Before 10:30 I'll take.
Yes, ma'am. Okay, ma'am.
Okay. Then Monday we'll have the class instead of tomorrow. Okay, just for tomorrow. Otherwise, Saturday, Sundays are fixed. Because
Yes, ma'am.
numericals part are left and those are very important. I've already segregated and I've already written the numericals. So those numericals part we'll have the discussion. Okay. So the graph part is important. This graph is the last thing. So how the graphical question will come to you in the exam? Question will be saying determine the Planck's constant, determination of Planck's constant and work function. This is how the question comes. So if we write the equation of kinetic energy, that is h nu minus the work function, right? So kinetic energy is written as EV naught, which is h nu minus work function. If we divide it by E, so this gets cancelled. We get V naught is equal to h by E into nu minus phi naught by E. So if I equate it with the equation y is equal to mx plus c, on the y-axis, see, we are getting y, on the y-axis we are getting the stopping potential. Then this is the slope of the graph. Slope of the graph. So see, this is the equation of a straight line. It means we are getting a straight line curve. And on the x-axis, I'm plotting the graph between incident frequency and stopping potential. So if I will calculate the slope of the graph, this will be equal to h by E. The slope of the graph will be equal to h by E. This is m is the slope, h by E. On the x-axis, we have the frequency and the y-intercept. That is, it is intercepting the y-axis. So at the y-axis, this is phi naught by E. But since this is minus, so this we are plotting it here. So this is minus phi naught by E. Now, what all things you have to remember from the numericals perspective and what all things we didn't discuss in the class. Firstly, slope will be equal to tan theta. So if you have any idea about tan theta, then you can equate it to h by E. Understood? H by E directly you can intercept it. Sometimes in questions I have seen it is given as electronic charge multiplied to magnitude of the intercept on vertical axis. So this is how work function can be determined. All right, so this is important. This you have to keep in mind. One more thing, one more formula let me discuss because that will be used in the next class. That is the formula of intensity of radiation. So this is basically intensity is always energy per unit area per unit time. So from here, energy per unit time. This is what we call as, what do we call this? Energy per unit time. Any idea? Energy per unit time. Try to recall. Power. This is power because you have some questions that came in the sample paper of 2013. Intensity can also be written as power per unit area. Power per unit area. This is it. So these are the things which you have to remember. The conversion, that is 1 electron into joule will be utilized. Value of Planck's constant 6.63 into 10 to the power minus 34 joule seconds. Value of speed of light 3 into 10 to the power 8 meter per second. And the formula that we have discussed in today's class. One more formula. Number of photons emitted per second. That also. Number of photons emitted per second. This is also there. So number of photons is the power divided by energy. This is power divided by the energy, number of photons. This is power and this is energy. That's it. These all will be used. You can quickly note down this.